This lecture, we're going to start talking about some aromatic molecules. Now, in particular, the most famous one is benzene. So this first lecture is going to sort of be focused on benzene and benzene-like things. So, but really, this really falls in the context of aromaticity, and that's going to be the overarching theme of the next few lectures. So benzene and aromaticity. If you recall, we describe benzene not as one 6-membered ring with alternating double bonds and single bonds, but as two resonance contributing 6-membered rings with alternating double bonds and single bonds. It reminds us that we can draw those double bonds in any particular orientation. Now, before we talk about the chemistry, let's just bring up some interesting history. This molecule was first discovered by Faraday of sort of the physics equations in the 1830s. And my notes remind me that I should, include names. So Michael Faraday. So sometime in the 1830s, benzene was discovered by Michael Faraday. Now, that doesn't mean that we knew what benzene was in terms of its structure. In fact, it took several years for the structure of benzene to be deduced, and that was between 1865 and 1872. A correct structure, and by correct I mean we were still developing our understanding of resonance and that sort of thing in bond line structures, but more or less a correct structure is proposed by Kekulé. So Kekulé, of our Kekulé structures from Organic Chemistry 1, is the first to propose the correct structure. Now, Kekulé, let's just appreciate this. It took about 35 years at least for this structure to be proposed. Now, Kekulé had some challenges he had to work through. So first of all, let's appreciate that benzene has a molecular formula of C6H6. What that tells us is that we have approximately 4 sites of unsaturation. That is, from a fully saturated molecule with all of its hydrogen atoms, we have 4 sort of distinct units of unsaturation that we have to be aware of. Let me just get some pages here. Excuse me. So we have 4 sites of unsaturation, but we have 6 carbons. So this is hexane with 4 sites of unsaturation. Now, what made this tricky is that when we dive a little bit into the chemistry of this, some interesting things started to emerge. So, I mean, hexane, let me just say this, hexane with 4 sites of unsaturation, that could be a straight chain with 4 double bonds in it. So we could have hexane 1, 2, 3, probably, if we do want to do this, sure, but it has to be linear. Okay, so there are ways to find, to introduce sites of unsaturation. But here's kind of the issue. If we have C6H6 as we know it, we try to do any chemistry on it, it turns out it's really hard to do most alkene chemistry on it. And that's going to be a big part of what we talk about in this unit. But if we add Cl2 and we apply a lot of heat, alkenes should react. But all we ever see is a little bit of C6H5 Cl. C6H5 Cl. So this is like just Cl addition, or Cl addition or substitution for an H. Now, that's not how alkenes react. In our previous structure where I have a bunch of double bonds, obviously we know that's not benzene, but back then they're trying to think about, okay, what do sort of molecules with unsaturation typically do? Well, they add 2 chlorine atoms, but there wasn't any C6 whatever I'll put H4, C6H whatever, and Cl2. There was none of this. So first of all, we have to say that was not observed. And there were only trace amounts of this monochloro addition. So this didn't make sense in the context of what we understand about alkene chemistry. Now, more importantly, what was weird about this trace product was there was only one product ever. So you only ever saw one product when you added one chlorine atom to this mysterious C6H6 molecule. So that suggests that one site is more reactive or that all sites are the same. And by sites, I mean sites of unsaturation. So this indicates that one site of unsaturation is more reactive, or there is only one site of unsaturation. Now let's take a second to think this data through. So this is the interpretation. If we see one chlorine atom adding, what they're saying is we have 4 sites of unsaturation. Now that if we only get one product, that means that one site is more reactive or that all sites are the same. Now, if we look forward in time and think about what benzene is, benzene has one site of unsaturation from the ring. Okay, and 3 sites from the double bonds. And by sites, I mean, these are our sites of unsaturation. These are the things that when we introduce them into our molecule, they lead to the deletion of 2 hydrogen atoms. That is to say, if you take hexane and you clip the ties, you tie the ends together, you're going to delete 2 hydrogen atoms. That's a site of unsaturation. Every time you introduce a double bond, add a double bond, you need to delete 2 hydrogens to avoid breaking the octet rule. So what we know is that the double bonds are all the same. And they are more reactive than the ring. And so what we're actually getting when we heat this up, if we could apply the structure, is we're taking Cl2 and we're applying heat. And it turns out that what we're doing is we're replacing one of the hydrogens with Cl. But that hydrogen could be any of the 6 hydrogen atoms. That's why we only observe one product. I don't know how to communicate this in our notes, so I'm just going to write this here. Kekulé didn't know this. Like maybe if you haven't thought about it, let me just say, if we look at our benzene starting material in that Cl2 reaction, because I can draw the double bonds anywhere, all of the carbon atoms are the same. All of the hydrogen atoms are the same. Okay, if you think through that, you can see this symmetry throughout the molecule. You can slice it in half in several directions. Okay, there's 6 planes of symmetry separating each of the bonds between the carbon atoms. That's going to make each of the carbons and each of the hydrogens the same, or in the same chemical environment. So doing a reaction at one is like doing the reaction at all the others. But Kekulé didn't know this until Kekulé has a dream. At least that's how the legend goes. So he has a dream about the Ouroboros. I think I'm going to spell this right. Ouroboros. The Ouroboros is the snake eating its tail. I don't know much about the history of this. But Kekulé has a dream about an Ouroboros, and it's a snake eating its tail. So we could, we could try to sketch a picture of this. All right, so there's the snake head. And I don't really want to, I guess the tail is not in the mouth. So how do we indicate that the snake is eating it? We could say yum here. There we go. Very good. Okay, so Kekulé has this dream and he realizes for the first time ever that the molecule is like the Ouroboros. The tail is biting the head. So Kekulé proposes a ring structure. Okay, Kekulé proposes a ring structure. Molecules have rings, and we start to understand, at least take our first steps towards understanding resonance. So this is what Kekulé proposes. So the proposed structure. Now this blue circle in the middle, this suggests the 3 pi bonds extend over all 6 atoms, and they can be drawn in any way. Or like, you could have the alternating double bond starting at one position or another position, which is what we kind of talk about. So overall, not overall, but over all 6 carbon atoms. This is a significant breakthrough in our understanding of molecular science because this tells us that molecules can have rings. Additionally, we take our first steps towards resonance structures. So it was Kekulé recognizing that one of the 4 mysterious sites of unsaturation can come from a ring. Now, that was in, let's see, if you remember, 1865 to 1872. It was Linus Pauling then in the 1930s. So Linus Pauling in the 1930s says that benzene is an average of 2 structural forms. And so this is where we say that we could draw benzene this way or this way, where the alternating double bonds and single bonds could be drawn in either orientation. Now, if we're an average, then what this means is that the bond lengths may not look like your typical bond lengths from what you would expect. Excuse me. So what he suggests is that the CC bond lengths are all the same. Are all the same really, no matter if you have a double bond or a single bond drawn between the atoms. Okay, so I'm just going to take a second while this is in front of us. I'm just going to emphasize this is Pauling, and this is equivalent to what Kekulé said. Kekulé said, I don't know where exactly to draw the double bonds because they sort of exist over all of the carbon atoms. Now, these two collectively suggest that benzene is this average of these 2 structures. And so if we have a CC single bond length, that's typically 1.54 angstroms. This is going to be like 1.3 angstroms, okay? Now, because we have an average of two structural forms where the double bonds and the single bonds are always alternating, but they could be drawn at different positions, this turns out to not be the case. Okay, so I'm going to cross these out, and instead I'm going to write in what we actually see in benzene, and that is that we have a 1.39 angstroms at all CC bonds. So this is really cool. It's not as low as 1.3, it's closer to 1.4, but it's not as high as 1.5, it's less. So it's somewhere in between a bond that's a double bond and a single bond, just to remind us, again, the power of resonance structures. Yes, sometimes it kind of looks like there's a double bond in the northwest corner. Sometimes it's a single bond. I mean, it's not really sometimes, it's some depictions have this double bond and some depictions have this single bond. They both are sort of right and sort of wrong. The actual structure is determined by the nuclear positions of the molecule, which shows that we have a distance of about 1.39 angstroms between all of the carbon atoms. All of the carbon atoms, all of the hydrogen atoms have the same bond lengths in benzene, and that's not that shouldn't make sense from one structural depiction, but rather two structural depictions that are averaged with each other. So we can capture some of those thoughts because benzene is an average of two bond line structures. There are more, but those two bond line structures are the greatest contributing. It's an average of two bond line structures. All CC and CH bonds have the same length. And it's the CC bond length that's interesting because sometimes in a structural depiction, you'll see a double bond and sometimes you'll see a single bond. Okay, so what I'm going to end with is a little bit of, you know what, I'm going to save it until the next lecture. I was going to do a little bit of naming, but we'll just put the naming in the next lecture. We'll let this be sort of the history of benzene. So we'll stop here and we'll pick this up next time. Until then, I'll see you next time. Okay.